got 1175. DP673, DP672. I know there's cars out there.
In railroading vernacular, the acronym DP stands for Distributed Power, or sometimes called Distributed Power Units, or DPUs. Distributed power are locomotives that are placed at the rear of a train or at midpoints of a train, or both. DPUs are typically used for super long trains, usually exceeding 10,000 feet, to prevent derailing and or exceeding the draw gear strength. Other benefits of DPUs are minimizing run-in and run-out of coupler slack throughout the train, as well as reduced draft forces along a train, which in turn reduces the lateral force between the wheel and rail on curves, thereby reducing fuel consumption and wear on various running gear components. Faster braking is another benefit of DPUs. When all of the brakes are at the front of a conventional train, it can take several seconds for pressure changes to spread to the rear. Under distributed power operation, the brakes are set at remote locomotives simultaneously with the command initiated on the lead locomotive, providing more uniform braking throughout the train. DPUs should not be confused with helper locomotives, which are added to help move heavy tonnage, usually over grades. And therein lies the difference between the two. Distributed power locomotives, or DPUs, is the actual head-end power needed to get the train's tonnage from point A to point B, albeit spread out through different parts of the train. Helper locomotives are extra locomotives that are needed to get the train and its head-end power, which sometimes includes the DPUs, over a specific portion of the railroad, usually an upgrade. After the closing of the former Southern Railway's saluted grade in North Carolina, the maximum grade that's seen on U.S. railroad main lines today is about 2.2%, which back in the steam days would increase the locomotive's effort by a whopping 880%. With that as a comparison, as small as a 0.1% grade may seem, in those same steam engine days, it could increase the amount of locomotive power needed to go uphill by as much as 40% compared to that of level track. Here in northeastern Pennsylvania, on the 10-mile climb from Taylor to Clark Summit on the Norfolk Southern Sunbury line, the ruling grade is said to be 1.54%. Once negotiating the grade at Clark Summit, the ruling grade of the Pennsylvania cutoff is 0.55%, and, once again, back in the steam days, increased the locomotive power required by a whopping 220%. And now, with all of that locomotive technical knowledge as background, you can see what today's modern locomotives have to deal with. It wasn't that long ago that you saw this train, and I mean that statement literally and figuratively. It's the train 37T, or at least it was. It was abolished back in 2020. What I didn't tell you about this train was that it stalled about 2 miles up the line. What a surprise. But to be fair to NS, it wasn't caused by human error this time around, but instead mechanical error. The third unit, the Dash 944 CW number 9610, malfunctioned upgrade and brought the train to a complete stop. In response, the K79 local switcher had to take their power, tack onto the rear of the 37, and nurse the disabled train to Clark Summit. But how does that old saying go? Those who fail to learn from history are doomed to repeat it. We've seen a lot of that old adage here on this channel. Today, another Train 11Z, more than 18,000 tons and more than 2 miles long, suffered the same fate. As you watch this multi-mile long giant lumber past, pay close attention to the radio chatter. DPUs are locomotives that operate remotely, placed in the middle or at the end of a train to provide additional power and improve train performance. They are designed to work in conjunction with the lead locomotive, receiving control commands and operating independently. The key benefits of DPU operation is to allow for longer trains with more horsepower without the excessive stress on car couplers, enhance train acceleration and braking performance, and reduce draw gear draft forces, enabling larger trains without compromising the infrastructure, and to enable more efficient train operations, particularly on steep grades. In summary, distributed power units, also known as DPUs, are remotely controlled locomotives that enhance train performance and enable longer trains and reduce infrastructure stress. While they present some operational challenges, their benefits have led to widespread adoption in the railroad industry. The Union Pacific Railroad, along with the BNSF, uses DPUs extensively, particularly in the western United States, to haul heavy trains up and over the steep grades. All other Class 1 railroads also employ DPUs in various applications. DPU is becoming a fact of life with the stupidly long trains that Class 1 railroads are running these days, especially in the winter when it's difficult to hold brake pipe pressure. Distributing the power helps to avoid breaker parts on these 130-plus car trains. For those unaware, the air compressor on EMD locomotives, except for the SD70 ACE T4, is directly driven by the diesel engine's crankshaft. The faster the engine revs, the more air it pumps. GE units have electrically driven compressors. The EMD 60 and 70 series locomotives will automatically rev up to about notch 4 as needed to try to maintain MR pressure, and Canadian National's SD70 M-2 will go a couple of notches higher than that to what sounds like notch 6, but even this is often not enough to maintain the proper MR pressure when charging a train in cold weather or compensate for a large leak on the locomotive, like the MR drain spitter valve or the air dryer sticking. DPUs can be single units or multiple unit consists depending on the application, and there's a couple of ways that distributed power is used on a train. Wired systems use existing train cabling for communication and control. Wireless systems employ radio frequency or RF connectivity for remote control. Despite the advantages, there are a couple of disadvantages to using DPUs. The additional operating time that's required to add or remove the DPUs is a big one. The costs that are associated with equipping the locomotives with remote control apparatuses is another. And then there's always the potential for the intermittent loss of the telemetry signal when running these multi-mile long trains. Someone shared with me the step-by-step procedures that the BNSF uses to set up their locomotives for DPU operation. Now, I'm not an engineer, so I don't know how accurate this setup is, but if there are any BNSF employees or railroad employees that can tell me whether or not this is actually how it's done, let me know in the comments.
Number 6227-6227 to the T&E MS 1019 South SOUTH at Taylor. Number 2, Box 2 is approach in CP 679, but 679 to CP 697. 697 on main MAI and track. 6227, one box summary number 2, dispatcher RKH.
Sorry, 6227, that is 6227, to the DNE NS 1019, south is NS 1019 at UTH at Taylor. One box check back to proceed from CP 679, that is CP 679 to CP 697, that is CP 697 on the main MAIN track. Check 6227 with one box check back to got by Horton over.
6227, one box family number 2, copied by Horton, is located at 12:35, 12:35 p.m.
X46227 with 1 box check back 2, copied by Horton, okay at 12:35 p.m. This is 1235 p.m. Finish our gauge. Ready, copy.
Step 1. Either couple the two power sets together or situate them in the train as desired. Either way, power sets must be attached to the same brake pipe. Step 2. Condition the controlling unit for the remote set. This includes: turn the isolation switch to run, turn the dynamic brake circuit breaker to on, turn the control and fuel pump switch to on, turn the engine run switch to on, turn the generator field switch to off, put the throttle handle in the idle position, put the reverser in the centered position, set the air brake setup switch to lead cut in or lead freight, put the automatic brake handle to continuous service, put the independent brake handle in the fully applied position. Step 3. Set up the controlling remote locomotive for distributed operations. This is done on the right-hand control screen. Select Distributed Power. Select Remote Setup. Enter the number of the controlling lead locomotive. Select Same or Opposite, telling the system which way the controlling distributed unit is facing compared to the lead unit. Verify whether the computer has your previous selections correct. Verify DP enabled lead cut in for EMDs or distributed power remote lead freight for GEs. Place the independent brake handle in release. Step 4. Condition the lead controlling locomotive by setting all controls to the same position you did on the remote set. Step 5. Using the computer screen on the lead locomotive, link the lead power set to the remote set. That means select Distributed Power, select Lead Setup, enter the number of the controlling remote unit and select Link. Verify the link for all remote units and press Accept or Done. Clear Distributed Power penalty by following display screen instructions. Step 6. The brake pipe test. Use the brake pipe to confirm the two sets are in the same train. When prompted, move brake handle to release. When the system reports ready for brake pipe test, press BP test and then select Execute. When prompted, move automatic brake handle to the minimum reduction position. The test will conduct itself automatically and may take up to 90 seconds to complete. The system will report BP test OK if successful. If not, repeat the test procedure. I'm not 1,000% sure of the year, but I believe it was back in 2010. The Union Pacific quietly ran a record-setting monster freight train over its Sunset route from Dallas to Long Beach using the 3.5-mile-long behemoth during a one-time test of the new distributed power configurations that may help to make long trains even longer. DPUs are used in both mid and rear train applications for multiple reasons. One reason I'm told for DPUs, especially the mid-train DPUs, might be to separate the loads and the empties. Now, I don't know if that's true, but I've been also told that the general rule of thumb for railroad operations is to put all the loads directly behind the lead units. Again, I don't know if that's true or not. What I can tell you here on the Norfolk Southern is that you can typically tell the length of a train by where the DPUs are placed. Longer trains have the DPU placed in the middle of the train, whereas shorter trains have the DPU at the end of the train. Recently, we've been seeing one-by-one operations where there's been one locomotive up front and one on the end, or even one in the middle, for a 1-by-1-by-0 combination. Although some trains may have the empties behind the DPs when used in a mid-train configuration, you can have loads and empties in between the DPs. It's placement of the loads and or empties, as well as the type of the car, if loaded or empty, is determined by the railroad rules, which is known as the car placement and train makeup restrictions. It's also determined by the DP's power rating. Too much power can jackknife empties or long or short cars under certain conditions. There are all sorts of formulas used to determine the proper placement. In any case, it cannot be more than 8,500 feet from the head consist. That's what I'm told. Any other remote consist behind that one cannot be more than 6,000 feet from it. That's also what I'm told. This is due to the data radios being used. Again, that's what I'm told. Air is important, obviously, but mid-train DPs on long trains are still a pain in the rear end, as the air has to pump to the rear of the train as well as towards the head end, and the head end is still pumping towards the DPs. This means that your air will recharge quicker on the front half, but may still take quite a bit of time to fully build behind the mid-train units. Weather is also a factor, as I mentioned earlier. The colder it is, the harder to pump the air. You will typically not see more than 2 units on the rear of a DP train online due to the power limitations, the jackknifing that we talked about earlier. If you do see 3, it's usually due to one breaking down and they just tacked on another unit out of convenience. Per rules, it's supposed to be set out at the next facility that can repair that engine. A good example of that is the Train 11Z that I recorded last year with 3 DPUs on the rear. Only the SD70 ACC was actually online, as the trailing 2 GEs were dead in tow. DPUs are unmanned and controlled by the lead locomotive. The engineer can run the train for the remote units to follow the throttle and dynamic brake commands at the same time as the lead, or can what is called fence the remote units to do something different. This is common in undulating grade where the train may be at different elevations at the same time, so using this fence will help reduce in-train forces. Here on the East Coast and in some metro and industrial areas, some local trains will have a locomotive on the rear. The locomotive is just along for the ride and is not in a DPU configuration. It's there to avoid having to run around the train if it needs to change direction. It's basically there for convenience. Switching in many highly industrialized areas have very little track capacity to turn locomotive power or to run around the train. We talked about that some videos back. Distributed power technology has been around since the 1970s, but only recently refined. The Southern Pacific and the Southern Railroad used local control with varied levels of success. The Burlington Northern tried it out as well and had all sorts of issues like the rest. It went from the dials to desktop boxes and now is integrated into the locomotive control screens. The original radio and control equipment required extended noses to house it. Those noses were known as Snoot noses. Snoots are the extra long noses on EMD SD40 locomotives, most notably the SD40-2 and the SD40T-2. Snoots were mainly used by the Western railroads like the Southern Pacific and the Union Pacific to house radio control equipment for DPU-style operations in the 1970s, 80s, and 90s. Canadian railroads such as the Canadian National and the Canadian Pacific also had snoots, but I don't think that they were ever used for DPU service. Canadian National SD40-2 number 6022, shown here on Penobscot Mountain in 2003, has the long snoot nose. Having just got off of that locomotive that day, I can tell you that the snoot nose did not hold any radio control equipment, but it did house a really nice bathroom. Note that there is no access door on the nose. What I cannot remember is why Engineer Colra is sitting in the conductor's chair. That's Conductor Richard Moore climbing on board. A few months back, I did a video on the last tunnel motor locomotive on the New York Susquehanna and Western. Number 3014 is an ex-Southern Pacific unit and also has the snoot nose. Here's a snippet from that video. On the SP, the snoots were used to house locotrol and or radio control equipment that was used in mid and or rear end train helper service. The access door on the conductor side of this snoot most likely gave entry to that radio control equipment. Closer to home, the regional Reading and Northern has 2 ex-Union Pacific snoots on their roster. SD40-2s number 3056 and 3058 both have the 116-inch long nose and the access door on the nose. The local Lehigh Railway has 2 ex-Canadian Pacific snoot nose SD40-2s on their roster. Numbers 4700 and 4721 Like the Canadian National 6022 that we just saw earlier, are long noses that do not have the access doors on those noses. Last but not least, Canadian Pacific number 5690, which I talk about a lot on this channel, had the long snoot nose, and like all the other Canadian snoots that we've seen in this video, was devoid of any access doors on that nose. I recall an article in Trains magazine some years ago which mentioned the problems that KCS was having with mid-train power causing a bunch of derailments. At the time, the mid-train power was usually placed 2/3 of the way back from the front end, primarily to equalize brake response time. After another derailment, a mid-level manager crunched the numbers and developed a chart for the best positioning of mid-train power under a variety of circumstances. Lately, they've tried to put the large setouts on the rear of the train, behind the DPs. If the train also picks up at the same yard, they may pick up behind the DPs. It depends on where the cars picked up are going and further work scheduled down the road. They've gone to trying to do the work off the rear end because the setouts and pickups are, more often than not, very large. It's just easier, and you could say safer, to pull through a yard track, cut off as much as will fit, and double over what doesn't to another track. The idea of doing that is that the conductor does not have to ride the side of the car for a long shove when holding on to 50, 75, 100, or even more cars. It defeats the purpose if the yard decides that it's easier for them if you pull by and then shove in. Then you're holding on to the entire train and shoving that train in. The conductor riding the side of a car at the end of that 100 car setout on the rear plus the 100 cars going through. I've heard that over on the CSX A&WP subdivision there has been some changes. At first it was a 1x1x0. The mid-train locomotive was almost always at full throttle or full dynamic. North of there, going northbound, was the ruling grade for the subdivision with a sag just south of the ruling grade. Now most times, except for much shorter trains, it's a 2x1x0 DPU configuration. On videos I've seen on the Montana Rail Link, I've seen coal and oil trains that were being operated by the BNSF with 2 or 3 locomotives up front, 4 or 5 Montana Rail Link helpers that were manned mid-train, plus another locomotive, usually BNSF, as the DPU trailing at the end of the train. Now how that operation works I don't know, but these trains operate in mountainous country where the radio communications I'm guessing are poor, so I'm not sure exactly how they pull that little trick off. The term push-pull operation is a term that's more often than not totally understood in the railfan community. Usually, when you hear someone refer to a train as a push-pull train, they'll be talking about having a locomotive on both ends of that train. And although this is technically accurate, it is not the only example of a push-pull train operation, as I'll explain. Push-pull train operation is a configuration for locomotive-hauled trains that allows them to be driven from either end of the train, whether having a locomotive at each end or not. That's important. One example of a push-pull train is a train that has a locomotive at one end of the train that's connected via some form of remote control, such as a multiple-unit train control, to a vehicle equipped with a control cab at the other end of the train. The second vehicle may be another locomotive or an unpowered control car. This is the type of push-pull operation that you typically see on commuter trains in heavily populated urban areas on lines such as the SEPTA, the New Jersey Transit, and the Metro North here in the Northeast. Despite the appearance, the two out-of-place Canadians on this train, which has just come out of the Allentown Yard and over the Lehigh River and into Bethlehem, Pennsylvania, are technically not in push-pull operation mode, but rather in pull-pull operation. The friendly engineer pulled the train out of the yard, dismounted, walked to the rear of the train, and boarded the SD70 M-2 to proceed westbound over the former Lehigh Valley and Reading lines. And did you notice that EOT device on the M-2? If not, go back and take a look again. This is why I call the M-2 end of the train the rear of the train. It's December 15, 2017, and it's just another typical dreary gray overcast day in eastern Pennsylvania. Pay attention to that date because it's important. Remember I told you to remember the day, December 15? Hot off of the memory card, I shot this train yesterday, 6 years later, to the day, on December 15, 2023. The train is the Roanoke, Virginia to Binghamton, New York bound 10Z, and is pretty much the former 14R, which became the 14Z for about 2 weeks in 2020, then became the 12Z, and now the 10Z. Who can keep up? At around 50 degrees with clear blue skies and not a trace of snow to be found, today's weather is a definite upgrade to that of Bethlehem's back in 2017. But the reason that I had to include this train in this video, besides the coincidental date of course, is the power. Distributed power, sometimes called DP for short, is a generic term referring to the physical distribution at intermediate points throughout the length of a train of separate motive power groups. Such groups may be single units or multiple unit consists and are remotely controlled from the leading locomotive. This practice allows locomotives to be placed anywhere within the length of a train when standard multiple unit or MU operation is impossible or impractical. DP can be achieved by wireless RF connectivity or wired train line means. Wired systems now provided by various suppliers use the cabling already extant throughout the train that's equipped with electronically controlled pneumatic brakes. otherwise known as ECP. DP trains, or trains with distributed power, are now common on the NS-DNH lines. Today's train has an EMD SD70 ACE on the point and an ES44 AC GEVO on the rear. Back in the summer of 2020, I caught this RNN push-pull train, the YJPI, entering Taylor Yard to do this day's work. You may have noticed that the GP38-2 number 2010 wasn't providing any power. That's because it's being used today as a shoving platform, and that man at the helm is actually the conductor. GP38-2 number 2012 pushed this train all the way up from Pittston Yard and will pull the 2010 and any cars picked up at Taylor back to Pittston. In today's GEVO-saturated world that is modern Class 1 railroading, it's nice to know that you can still find EMD leading and sometimes dominating last ships out on the high iron. Union Pacific and our own Norfolk Southern are two such Class 1 railroads where EMDs are still in force. Today's train is another 10Z, which I recorded back on November 10 of this year, and is another example of push-pull distributed power operation. But another term that could also be used to describe this train is top and tail. A top and tail railway train has locomotives at both ends, oftentimes for ease of changing direction, especially where the terminal station has no runaround loop. This is a British term, and here in the USA, top and tail is also typically used to describe commuter and sometimes short local trains. In traditional top and tail operation, it's typically normal for only the leading locomotive to power the train. It's properly distinct from a push-pull train, which has a locomotive at one end and a control cab at the other end. Top and tail operation is also used for ballast trains, which have to move up and down a line undergoing track maintenance. It's safer to drive these trains from the front when operating in reverse. Are you confused yet? One last railroad term used for trains with locomotives on both ends is a term called bookending. Call them what you fancy, push-pull, top and tail, or bookending. The proper term is in the eye of the beholder. Each term has its own specific usage, while each term can be used universally in one way or another. Out on the main line is where these operations shine, and my thanks goes to conductor trainee Joe Green for the information on this train. Enjoy this train and watch it till the end, because the best part is coming up from behind.